Continuing our exploration of mechanisms involving triangles, we have what's called oxymercuration, where we add an oxygen to the more electronegative oxygen on the more substituted carbon. Whoa, that's not a pen. More electronegative element on the more substituted carbon. That's called Markovnikov. And the new groups are on opposite sides. Anti, that's stereoselectivity. And we've got a chemical, mercury II acetate. What's the II mean? Sorry, say again? Hg has a 2+ charge, correct? And that makes it what kind of a compound? If you got a 2+ ion and then 2 acetate ion, well, I think I gave the answer almost. What kind of compound is that? Ionic. Yeah. What happens to many compounds? Well, what happens to compounds that are soluble in water when you put them in water? Ionic compounds. What do they do to dissolve? They don't just stay the way they are, do they? What do? They split. I like that. That's a nice way to say it. Nice way to say split is ionize, right? Yeah, that's what the word she was looking for. No, your word was good though. Now, you've got a bond between mercury and oxygen, right? Now, don't be looking at the periodic table to answer this question. Which atom is more electronegative? Yeah, just say O. If you're asked to choose between an O and any other atom ever, there's only one time you're going to say the other atom is more electronegative. One, and it's fluorine, and we don't play with that very much in this course. So if O is bonded to something, it's more electronegative. So if I have to break that bond, where do the electrons go? Towards the atom that's pulling hard on them, or to the one that's not pulling hard at all? I mean, I just gave the answer. To the one that's pulling the hardest. It's going to grab the electrons and say, hey, when I'm around, you don't get electrons. There you go. So you get mercury ion that looks like this. Hg O2C CH3, and there's a plus here. And you also get O2C CH3 with a minus. That's called acetate, right? Acetate. And looking ahead, I just want, since we're on this kick, can you tell me the pKb? Tell me how to work it out first. You can just start by saying 14 minus. I need the pKa of what? Conjugate acid of acetate is called, starts with ACET and ends with IC acid. And what functional group is it? Acetic acid. What functional group is that? HO2CCH3. What functional group is that? Can't do the pKa if we don't know it's the functional group. Carboxylic acid. What's the pKa of a carboxylic acid? 5. So this one, compared to the previous example, is a much, 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 much better base. When I need a base, this is it. Right? Remember, water was what, 17? 14 minus -3. We chose -3. If you chose -2, it was 16. If you chose -3, it's 17. Either way you did it, those numbers are nothing compared to this number as a base, right? We're talking 100 billion times stronger base here than a water. So when I ask you what base are we going to use at the end, you're going to say, acetate, right? Okay. Right before the end. The end, I'm going to draw the Lewis structure for sodium borohydride. Okay, next up is triangle time, of course. This time the arrows making the triangle, I misspoke. The arrow making the triangle is that one arrow. 2 electrons in the pi bond react with the mercury to make a different kind of triangle. What do I mean by different kind of triangle? Well, it better be a different kind of triangle. How many electrons made the 2 bonds here and here? Well, this one made one of the bonds. It's got 2 electrons in it. This one made the other bond. It's got 2 electrons in it. Those are real bonds. Here they are. Triangle. Same story down here, right? Except Dr. Whitaker is going to be in trouble on the video. We're going to add a comment. I forgot the 3rd arrow. And embarrassingly, I also said you're going to be impressed at how similar they are, these 2 reactions at the beginning. And then I didn't do them the same. And I screwed up. Arrow comes back to which carbon? Try to use this kind of wording. Arrow comes back to which carbon? More substituted. Arrow came back to which carbon? Get the same answer. It's always the same answer. More substituted carbon. Here, we didn't have arrows coming back. We only had these 2 electrons. Mercury is a cation. It doesn't have electrons. Don't pretend it does. I've seen it many times. Every time it's been wrong. Okay? Mercury does not have a lone pair. Do not put a lone pair on Mercury. It does not have one. Okay, so you've only got 2 electrons making a triangle. This is a very different triangle. Here is the skeleton. Here is the triangle. These are not dashes. Not dashes. They are, in fact, partial bonds. HgO2CCH3, and the plus charge is, what am I trying to show? Where did I put the plus charge? I've never done that before. I put it on an atom every time before. What am I trying to say by putting it in the middle of that triangle? The plus charge is shared by 3 atoms. That's better than being on one little position. You're sharing the plus charge. You're sharing the burden of the plus charge. It's a burden. Having a charge is a burden. If you can share it with multiple atoms, it's less of a burden. Okay? And these are, just a note, 3 partial bonds. Remember, all 3 of them were made using only 2 electrons. So if you had to estimate and you pretended they were all equal, how much of a bond is each one? How many electrons are in each one? 2 electrons total in 3 partial bonds. Something times 3 partial bonds equals 2 electrons. What times 3 gives 2? The answer to our question. So each bond has this quote unquote bond. They're really partial bonds. 2/3 of an electron. That's a pretty weak bond, isn't it? So why is mercury so special? Why does this reaction happen so fast? This reaction is 10 times faster than the one on the previous page. And the one on the previous page is pretty fast. Both of these are pretty fast. But mercury, even faster. And the reason is the mercury is no normal element. It is an element with a mass close to 200 grams per mole. Hydrogen has a mass of 1 gram per mole. So right away, you know, mercury is a lot bigger, right? I mean, crude approximation, 200 times bigger. Okay? That means a single bromine atom can be simultaneously over both carbons, almost touching each one. That's how big it is. So you don't really think about triangle strain here, right? Because you got the two carbons and a big fat mercury sitting on top of both of them. It's like a lid on top of two carbons. All right, so it's got that going for it. It's got the shared charge, so it's got that going for it. It's a triangle, so what's next? Every time you make a triangle, here's the answer to this question. What's next after you make the triangle? Backside attack. Always. You make a triangle, what's your next step? Say it, you say it. Backside attack. And in this case, how do you get the OH on that carbon? Don't forget, you got to get to here. How'd you get it on last time? From what molecule? Water. We're coming down this way this time. Remember, water's everywhere, right? I got a keyboard somehow. I don't know how. Okay. And I don't have arrows to show a partial triangle breaking, so don't use it. I don't have an arrow for that. Partial arrow, I tried one semester. Students got confused. Just leave it at this arrow. It's a backside attack. And you're going to get something related to that product at the top of the screen. You've got your wedge. This is definitely related to that product at the top of the screen. You got your dash to a mercury, which has CH3, CO2 on it. And how do I get that to be that? How do I get that to happen? All right, here's your second chance. What's the relationship between these two molecules and what kind of reaction is it? Acid-base reaction, because they're a conjugate acid-base pair. The one with the extra proton down here is the acid. What's the best base we have available for taking that proton? Say it again. She may have said water, but she caught herself. What'd she say the second time? Acetate. Nice recovery there, young lady. All right. So I'm just going to copy the acetate down. pKb of 9 is 10 to the power of 8 better than water, which was pKb of 17. Previous video. Okay, and that finishes that off. And the side product would be acetic acid, right? So here's my side product. I took a blue H, and we had a green O2CCH3. That's acetic acid. I think somebody had a question. I'm missing a methyl again. What am I missing? And this goes, oh, I'm missing a methyl. Ethyl. My goodness. Sorry about that. There we go. Thank you. This carbon's right here. Yeah, there we go. Yeah, I had an ethyl just drop off. Sad. And acid base made acetic acid, pKa 5. Good story. And then I got to ask you, what am I doing on this next reaction? And how do I test you on the next reaction? Because we don't do the mechanism here. We don't do this mechanism. We don't do this mechanism. But you are responsible for knowing that it's this chemical that gets rid of the mercury and puts what in its place? If you're looking at the black H, I'm going to remind you that black H was there already. I'm just trying to show you there is a new H and it's green, right? So mercury got replaced by H. Using what chemical? Sodium borohydride, Lewis structure. Sodium is a spectator. Borohydride is the active ingredient. And what charge do you get on a boron when it has 4 bonds? It's in group 3. So when it has 3 bonds, it's neutral. Or no formal charge. Yeah. But here it has an extra bond. So it's sharing 8 is like owning 4. It owns 1 more electron here than there. When you own 1 more electron than you do on the periodic table, what's your charge? Minus. Hey, that's why it's listed second, right? NaBH4, cation, anion. And the name says the hydrogens are hydride. Just a quick reminder, this is a preview for our next video. 2.0 versus hydrogen 2.1. Less electron A. Okay, so really the formal charge here is misleading. It is a formal charge, but in terms of reality, it's really those H's that are all slightly negative. Okay? They add up in terms of the chemistry and electronegativity. It's the H's that are the negative. The name implies that, right? If you end with IDE, like sodium chloride, what charge does chloride have? Negative. Ides have negative. So the name implies those H's are negative. This doesn't. But the chemistry, if, you know, this is not, you're not responsible for anything down here. I should have told you, stop writing. You didn't need to write any of this down. The nature of borohydride is this. Hydrogen's there, and it's telling boron, I'm more electronegative than you. I'm just taking my electrons. I'm going home. And now you see how it got its name. What's that ion to the left? Hydride. Yeah, that's how BH4 negative behaves. It behaves like a hydride. There's the thing that's going to do chemistry right there. It's all extra, okay? But how do you get tested on this? I'm going to show you, and it's going to disappear. So pay attention. You can rewatch the video. I can ask about NaBH4 2 ways. Ready for the first way? On the test, I'll have a blank. Instead of NaBH4, I will have a blank right here. And NaBH4 is what you tell me. You put NaBH4 in there for a point, if that's the box. Okay? Control Z. Now, I can also have the box over here, in which case this is blank. And if that's blank, what are you going to put in the box? That. Okay? And that's your answer. So 2 ways to test NaBH4. 1, do you know what the chemical is that gets rid of the mercury and puts an H in its place? And you put this chemical down. 2, if you react this chemical with this chemical, what's the result? And you give me this chemical. Those are the 2 ways I'm going to ask. And that's it for this video.